Hello there. As you settle into the quiet embrace of the night, prepare yourself for a journey into one of the universe's most spectacular and violent events. Tonight, we're going to explore the final moments of a star's life, witnessing the extraordinary transformation that occurs when these cosmic giants die. We'll journey deep inside dying stars to understand the birth of supernovas, those brilliant explosions that briefly outshine entire galaxies and seed the cosmos with the very elements that make life possible. Before we begin this cosmic adventure, I invite you to like this video and subscribe to give me more motivation. Your support helps me continue bringing you these deep explorations of our magnificent universe. And now, let's drift into the dream of exploring the vast cosmos together with Astromind. So take a deep breath, relax, and let your mind wander among the stars as we unravel one of nature's most powerful phenomena. Chapter 1: The Life of a Star. To understand how a star dies, we must first understand how it lives. Every star you see twinkling in the night sky is engaged in an eternal struggle, a cosmic battle between two fundamental forces that has raged for billions of years. On one side stands gravity, the relentless force that wants to crush all matter into an infinitely small point. On the other side stands nuclear fusion, the process that converts lighter elements into heavier ones and releases tremendous amounts of energy in the form of heat and light. This balance, this delicate equilibrium, is what we call hydrostatic equilibrium, and it defines a star's entire existence. When a star is born from a collapsing cloud of gas and dust, gravity pulls the material inward, compressing it. As the density increases, so does the temperature. Eventually, the core becomes so hot and dense that hydrogen atoms begin to fuse together, forming helium. This is the fundamental process powering every star, including our Sun. The fusion reactions release enormous amounts of energy, creating an outward pressure that pushes against gravity's inward pull. For millions or even billions of years, depending on the star's mass, this balance holds steady. The star sits comfortably on what astronomers call the main sequence, converting hydrogen into helium in its core, shining steadily, providing light and warmth to any planets that might orbit it. Our Sun has been doing exactly this for approximately 4.5 billion years, and it will continue for another 5 billion years or so before its hydrogen fuel begins to run low. But the mass of a star determines everything about its life and death. A star's mass dictates how hot its core burns, how quickly it consumes its fuel, and ultimately, how it will die. Massive stars, those 10 times or more the mass of our Sun, burn through their fuel at prodigious rates. They shine brilliantly, radiating enormous amounts of energy, but this comes at a cost. They exhaust their hydrogen supplies in just a few million years, mere cosmic eye blinks compared to the Sun's 10 billion year lifetime. When a massive star runs out of hydrogen in its core, something remarkable happens. The core, no longer supported by the outward pressure of hydrogen fusion, begins to contract under gravity's pull. As it contracts, it heats up. The temperatures become so extreme that helium itself begins to fuse, combining 3 helium nuclei to form carbon in a process called the triple alpha process. This process was predicted by astronomer Fred Hoyle in 1954, and it represents a crucial step in stellar evolution. The temperature required for helium fusion is about 100 million degrees Kelvin, nearly 7 times hotter than the core of a main sequence star. The star now has a new source of energy, and it responds by expanding dramatically. Its outer layers swell outward, cooling as they expand, and the star becomes a red supergiant. If our Sun were replaced by a typical red supergiant, its surface would extend past the orbit of Mars, swallowing Mercury, Venus, and Earth in the process. Stars like Betelgeuse, the bright red star marking Orion's shoulder, are red supergiants. Betelgeuse has expanded to a diameter approximately 700 times larger than our Sunday. But helium fusion doesn't last long in massive stars. Helium burns for perhaps 1 million years in a star 15 times the Sun's mass, and then it too is exhausted. The core contracts again, temperatures rise again, and a new fusion process ignites. Carbon fuses to form neon and magnesium. The star is now structured like an onion, with shells of different elements burning at different depths. In the center lies the inert carbon-oxygen core, surrounded by a shell burning helium, surrounded by a shell burning hydrogen, all enveloped by the star's vast, cool outer layers. This process continues in an accelerating cascade. Each successive fusion stage requires higher temperatures and densities, and each stage proceeds more rapidly than the last. After carbon burning comes neon burning, which lasts perhaps a year, then oxygen burning, which might last just 6 months. Finally, silicon burning begins, fusing silicon nuclei into heavier elements. This final stage lasts approximately 1 day. Think about that for a moment. A star that has been shining for millions of years, that has slowly and methodically fused lighter elements into heavier ones through multiple stages, suddenly finds itself burning through its final fuel source in a single day. It's as though the star knows its time is running out, and it's desperately trying to postpone the inevitable. But inevitability cannot be postponed forever. Silicon burning produces iron, and iron is the end of the line. Chapter 2. The Iron Catastrophe. Iron sits at a special place on the periodic table, a place that dooms every massive star. To understand why, we need to understand a fundamental principle of nuclear physics: binding energy per nucleon. This concept, abstract though it may sound, determines the fate of stars. When lighter elements fuse together to form heavier elements, the process releases energy because the resulting nucleus has a slightly lower mass than the sum of its components. This missing mass has been converted into energy according to Einstein's famous equation, E equals mc squared. The energy released provides the outward pressure that supports the star against gravitational collapse. This works beautifully for hydrogen fusing to helium, for helium fusing to carbon, and so on up the periodic table. But iron 5-6, with 26 protons and 30 neutrons, has the highest binding energy per nucleon of any element. This means it's the most stable nucleus. Fusing iron into heavier elements doesn't release energy, it requires energy. Once a star's core is composed primarily of iron, nuclear fusion can no longer support the star. The game is over. The star has reached a point of no return. Picture the core of a massive star in its final hours. It's approximately the size of Earth, but contains more mass than our entire Sunday. The core is composed almost entirely of iron, heated to temperatures exceeding 5 billion degrees Kelvin. The density is staggering, about 200 billion times denser than water. A single cubic centimeter of this material would weigh more than 200 tons on Earth. The iron nuclei are packed so tightly that electrons are forced to move at speeds approaching the speed of light. The core is supported against gravity only by electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle. This principle states that no two electrons can occupy exactly the same quantum state. When matter is compressed to extreme densities, electrons are forced into higher and higher energy states. The pressure they exert trying to avoid each other creates the final barrier against gravitational collapse. But this barrier has a limit, calculated by astrophysicist Subramanian Chandrasekhar in 1930 during a sea voyage from India to England. Chandrasekhar, who was just 19 years old at the time, showed that electron degeneracy pressure can support an object only if its mass is below approximately 1.4 times the mass of the Sunday. This critical mass is now called the Chandrasekhar limit, and it represents a fundamental boundary in astrophysics. Chandrasekhar would later win the Nobel Prize for this discovery, though not until 1983, more than 50 years after his initial calculation. In our dying massive star, the iron core continues to grow as silicon burning adds more and more iron to it. The core contracts slightly under its own weight, becoming hotter and denser. Shell burning in the layers above the core continues, raining down more matter onto the core's surface. The core's mass creeps upward, approaching the Chandrasekhar limit. Then, suddenly, catastrophically, several things happen at once. The core temperature reaches approximately 5 billion degrees, and at these temperatures, high-energy gamma rays begin to break apart iron nuclei in a process called photodisintegration. The iron nuclei that the star worked so hard to create, fusing lighter elements through multiple stages over millions of years, are torn back apart into helium nuclei and individual nucleons. This process absorbs enormous amounts of energy that was providing pressure support against gravity. Simultaneously, electron capture begins to dominate. At the extreme densities in the core, electrons are forced into atomic nuclei, where they combine with protons to form neutrons and neutrinos. The reaction is electron plus proton becomes neutron plus neutrino. This process removes electrons from the core, and with them goes the electron degeneracy pressure that was holding the core up. Within less than a second, the core loses all support. Gravity wins the ancient battle decisively and completely. The core collapses. Chapter 3. The collapse. The collapse of a star's core is one of the fastest and most violent events in the universe. In less than a second, a core the size of Earth is crushed to a sphere perhaps 20 kilometers across. The material falls inward at velocities approaching 1/4 the speed of light, roughly 75,000 kilometers per second. To put this in perspective, imagine the entire mass of the Sun compressed into a ball the size of a small city, and then having that ball shrink to half its size in less time than it takes to blink. The violence of this event defies comprehension. Matter is falling inward so fast that if you could somehow stand at the edge of the collapsing core, you wouldn't see the center falling away from you. You would see yourself accelerating toward it at relativistic speeds. As the core collapses, the density skyrockets. Within milliseconds, the density exceeds that of an atomic nucleus, about 400 trillion grams per cubic centimeter. At this point, something extraordinary happens. The neutrons in the core, now packed essentially shoulder to shoulder, begin to exert a new kind of pressure, neutron degeneracy pressure. Like electrons, neutrons are fermions, particles that obey the Pauli exclusion principle. They cannot be forced too close together, and they push back against further compression. Additionally, the strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei, begins to play a role. At nuclear densities, this short-range but incredibly powerful force creates a repulsive pressure that opposes further collapse. The combination of neutron degeneracy pressure and the strong nuclear force brings the collapse to a sudden, violent halt. The inner core stops collapsing at a radius of about 10 to 20 kilometers, but the outer parts of the core haven't gotten the message yet. Information cannot travel faster than the speed of light, and in the case of dense stellar material, it travels at the speed of sound through that material, which is slower than light speed, but still relativistic. The outer core is still falling inward at tremendous speed when the inner core suddenly becomes incompressible. The result is a bounce. The infalling outer core slams into the now rigid inner core and rebounds, rather like a rubber ball dropped onto concrete. A shock wave is born at the point of impact and begins to propagate outward through the infalling material. This shock wave will, within the next few seconds, transform into the most energetic explosion in the universe, a supernova. But before we follow the shockwave's journey to the surface, we need to discuss one of the most elusive particles in physics, the neutrino. During the core collapse, an enormous number of neutrinos are created. When electrons are captured by protons to form neutrons, a neutrino is emitted for each conversion. Additionally, various nuclear reactions in the hot, dense core produce neutrinos through different channels. Within the first second of collapse, approximately 10 to the power of 58 neutrinos stream out of the core. This is such an incomprehensibly large number that if you tried to count them at a rate of 1 billion per second, it would take you longer than the age of the universe to finish. These neutrinos carry away enormous amounts of energy, approximately 99% of the total energy released in the supernova. To put this in perspective, the kinetic energy of the matter ejected in the explosion, the light the supernova produces, the cosmic rays it accelerates, everything we can observe, all of it together represents only about 1% of the total energy release. The other 99% streams away silently in neutrinos, invisible particles that barely interact with matter. Because neutrinos interact so weakly with matter, they escape from the core almost immediately, even though it's incredibly dense. Neutrinos can pass through light years of solid lead with only a small chance of interaction. But the core of a collapsing star is so dense, and there are so many neutrinos, that even these ghostly particles deposit a tiny fraction of their energy into the material surrounding the core. This energy deposition is crucial. The shock wave created by the core bounce doesn't have quite enough energy to blow apart the star on its own. As it propagates outward, it pushes through the infalling outer layers, and this requires energy. The shock wave loses energy as it goes, heating the material it passes through and dissociating iron nuclei back into lighter elements. Within a few tens of milliseconds, the shock wave stalls. It runs out of energy and gets stuck a few hundred kilometers above the surface of the newly formed neutron star at the center. For several tenths of a second, the fate of the supernova hangs in the balance. If the shock wave cannot be revived, the explosion will fail. The outer layers of the star will simply fall back onto the core, and instead of a spectacular supernova explosion, the star will quietly collapse into a black hole, leaving nothing behind but a faint burp of neutrinos. But in most cases, the shock wave is revived by energy from neutrinos. Even though neutrinos barely interact with matter, there are so many of them, and they're so energetic that a small fraction deposits enough energy in the region behind the stalled shock to heat it and push the shock outward again. Think of it as CPR for a dying explosion. The neutrinos breathe new life into the shock wave, and it begins moving outward once more. Computer simulations of this process have been ongoing for decades, and only in the past few years have simulations achieved the resolution and physical completeness necessary to demonstrate successful shock revival. These simulations require some of the world's most powerful supercomputers, running for months at a time, to model a few seconds of stellar collapse. The physics involved includes general relativity, nuclear physics, neutrino physics, magnetohydrodynamics, and radiation transport, all coupled together in highly non-linear ways. Recent simulations have shown that the revived shock doesn't expand smoothly. Instead, it becomes unstable, developing large convective plumes where hot material rises and cool material sinks. the flow becomes turbulent and asymmetric. This asymmetry is important because it gives the newly formed neutron star a kick, causing it to recoil at speeds of hundreds of kilometers per second. This explains why we observe many neutron stars moving rapidly through space, far from where they were born. Chapter 4: The Explosion. Once revived, the shockwave accelerates outward through the outer layers of the star, gathering speed as it goes. The shockwave is a discontinuity in the material, a thin region where pressure, density, and temperature jump to much higher values. Ahead of the shock, the material is still relatively cool and dense, still falling inward. Behind the shock, the material is intensely hot, compressed, and now moving outward at high velocity. As the shock moves through the star's onion-like layers, it heats each shell to billions of degrees. These extreme temperatures, maintained for several seconds as the shock passes through, trigger a final bout of nuclear fusion called explosive nucleosynthesis. This is where many of the elements heavier than iron are created. Remember that fusion reactions creating elements heavier than iron require energy input rather than releasing energy. Under normal circumstances in a star, such reactions don't occur because they would drain energy from the star rather than provide it. But in the extreme conditions behind the shockwave in a supernova, these reactions can proceed. The energy comes from the kinetic energy of the explosion itself, from the gravitational energy released during the collapse. The neutron-rich environment created by the electron capture during collapse is particularly important for creating heavy elements. Nuclei can rapidly capture neutrons, building up heavier and heavier isotopes in a process called the R process, where R stands for rapid. The R process is responsible for creating approximately half of all elements heavier than iron, including gold, platinum, uranium, and thorium. Every gold atom in every piece of jewelry on Earth was created in a supernova or similar cataclysmic event billions of years ago. The shock wave takes hours to reach the surface of the star because the star is so large. A typical red supergiant might have a radius of several 100 million kilometers, and even traveling at thousands of kilometers per second, the shock needs time to traverse this distance. As it goes, it deposits energy into the outer layers, accelerating them to thousands of kilometers per second. When the shock finally breaks through the surface, the star lights up. Within hours, the supernova becomes millions of times brighter than it was before. Within days, it reaches its peak luminosity, shining as brightly as 5 billion suns. If you could somehow replace one of the stars in a distant galaxy with a supernova, that single exploding star would, for a few weeks, rival the combined brightness of all the other hundreds of billions of stars in that galaxy. The energy released in a supernova is staggering. The total energy output is approximately 10 to the power of 46 joules. To put this in perspective, this is more energy than the Sun will emit in its entire 10 billion year lifetime. It's roughly equivalent to converting the entire mass of Jupiter into pure energy. The Sun's total power output is about 4 times 10 to the power of 26 watts. A supernova releases energy at a rate of roughly 10 to the power of 37 watts at its peak. The supernova outshines the Sun by a factor of about 10 billion. The material ejected in the explosion races outward at speeds of 5,000 to 20,000 kilometers per second, typically around 3% of the speed of light. This expanding shell of material, enriched with the elements created during the star's lifetime and in the explosion itself, plows into the surrounding interstellar medium. Over thousands of years, the expanding supernova remnant sweeps up more and more material from its surroundings, creating an ever larger bubble of hot, glowing gas. The shock wave from the supernova compresses the interstellar medium, and these compressed regions can trigger the formation of new stars. The supernova thus not only ends one star's life, but helps create the next generation of stars. The heavy elements ejected by the supernova mix with the interstellar gas, enriching it with carbon, oxygen, silicon, iron, and all the other elements necessary for planets and life. Over cosmic time, as generation after generation of stars live and die, the universe slowly becomes enriched with heavy elements. The earlier stars, formed just a few 100 million years after the Big Bang, contained almost no heavy elements. They were composed of the primordial hydrogen and helium created in the Big Bang itself, but each generation of stars that lived and died added more heavy elements to the cosmic mix. Our Sun is relatively rich in heavy elements, containing about 2% of its mass in elements heavier than helium. This may not sound like much, but it's crucial. Without these heavy elements, rocky planets like Earth could not exist. Carbon, oxygen, silicon, iron, the atoms that make up rocks, oceans, atmosphere, and life itself all came from stars that died long before our solar system was born. Astronomer Carl Sagan famously said, "We are made of star stuff," and he was absolutely right. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon that forms the backbone of every molecule in your body, all of it was created in the furnaces of stars and scattered into space by supernovas. We are, quite literally, the ashes of long-dead stars. Chapter 5. What's left behind? When a massive star explodes as a supernova, most of its mass is blown into space, but the core remains behind. What happens to this core depends primarily on its mass. If the core's mass is between approximately 1.4 and 2 or 3 times the mass of the Sun, it becomes a neutron star. These are among the strangest objects in the universe. A neutron star packs the mass of the Sun into a sphere just 20 kilometers across. The density is approximately the same as an atomic nucleus, around 400 trillion grams per cubic centimeter. A single teaspoon of neutron star material would weigh as much as Mount Everest. At such extreme densities, matter takes on exotic properties. The surface of a neutron star is thought to be crystalline, a solid crust of iron nuclei arranged in a lattice, but with densities millions of times greater than any material on Earth. Below the crust lies a superfluid of neutrons, a quantum liquid with zero viscosity that can flow without friction. Deeper still, at the very center, the conditions might be extreme enough to break neutrons down into their constituent quarks, forming what physicists call quark matter. Neutron stars are born spinning rapidly, often rotating hundreds of times per second. They also possess intense magnetic fields, typically 1 trillion times stronger than Earth's magnetic field. These magnetic fields channel radiation from the neutron star's surface into narrow beams that sweep through space as the star rotates, rather like a cosmic lighthouse. If Earth happens to lie in the path of one of these beams, we detect regular pulses of radiation, and the neutron star is called a pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge University. She detected regular pulses of radio waves, arriving with extraordinary precision every 1.337 seconds. The regularity was so perfect that the team briefly wondered if they might have detected signals from an alien civilization and nicknamed the source LGM-1 for Little Green Men 1. But soon more pulsars were discovered, and it became clear they were natural phenomena. Bell Burnell's discovery opened an entirely new field of astrophysics, though controversially, she was not included when the 1,974 Nobel Prize was awarded for the discovery. Over time, A neutron star's rotation gradually slows as it loses energy, and its magnetic field weakens. After a few 100 million years, most pulsars have slowed down so much that they no longer produce detectable radio pulses. They become invisible, silent neutron stars drifting through space, no longer announcing their presence with regular pulses. But if the core's mass exceeds approximately 2 to 3 solar masses, not even neutron degeneracy pressure and the strong nuclear force can halt the collapse. The core continues collapsing, shrinking past the point of no return, past what's called the event horizon. It becomes a black hole. The formation of a black hole from a collapsing stellar core is one of the most extreme events in physics. The core's escape velocity, the speed needed to escape its gravitational pull, exceeds the speed of light. Since nothing can travel faster than light, nothing can escape from within the event horizon. Not matter, not light, not information. The core has, quite literally, cut itself off from the rest of the universe. The Schwarzschild radius, which defines the size of the event horizon for a non-rotating black hole, is proportional to the black hole's mass. For a black hole of 5 solar masses, a typical mass for stellar black holes, the Schwarzschild radius is about 15 kilometers. This is roughly the size of a small city, yet it contains 5 times the mass of the Sunday. At the very center of the black hole, general relativity predicts a singularity, a point of infinite density where the known laws of physics break down. However, most physicists believe that quantum effects, which are not included in general relativity, will prevent the formation of a true singularity. A complete theory of quantum gravity, which physicists have been seeking for decades, would be needed to describe what really happens at the center of a black hole. Several candidate theories exist, including string theory and loop quantum gravity, but none have been conclusively confirmed. From outside the black hole, however, we need only general relativity to describe what we see. The black hole has only 3 properties: mass, charge, and angular momentum, spin. Everything else about the star that formed it, its composition, its structure, its history, is erased. As physicist John Wheeler put it, black holes have no hair, meaning they have no distinguishing features beyond these 3 numbers. Black holes can grow by accreting matter from their surroundings or by merging with other black holes. When a black hole is in a binary system with a normal star, it can pull gas from the companion star. This gas spirals inward, forming an accretion disk around the black hole. Friction in the disk heats the gas to millions of degrees, causing it to emit X-rays. These X-ray binaries were among the first stellar black holes discovered. Recent advances in gravitational wave astronomy have opened a new window on stellar black holes. When 2 black holes orbit each other, they emit gravitational waves, ripples in space-time itself. As they lose energy to gravitational wave emission, their orbit shrinks and they spiral closer together. Eventually, they merge in a violent collision that produces a powerful burst of gravitational waves. The LIGO and Virgo detectors have observed dozens of these black hole mergers since the first detection in 2015. These observations have revealed that stellar black holes can be more massive than previously thought, with some weighing 30 or 40 times the mass of the Sunday. They've also provided the most stringent tests yet of general relativity's predictions about strong gravity phenomena. Whether a supernova leaves behind a neutron star or a black hole depends on several factors, including the mass of the progenitor star, its composition, its rotation rate, and details of the explosion itself. Current models suggest that stars with initial masses between about 8 and 25 solar masses produce neutron stars, while more massive stars produce black holes. However, there's still considerable uncertainty in these numbers, and the dividing line between neutron star and black hole formation is an active area of research. Chapter 6: Different types of supernovas. Not all supernovas are created equal. While we've been discussing what astronomers call Type 2 supernovas, or core collapse supernovas, there are other types of supernova explosions, each with its own mechanism and characteristics. Supernovas were originally classified based on their spectra, the pattern of light they emit at different wavelengths. Astronomers found that some supernovas showed strong hydrogen lines in their spectra, while others did not. Those with hydrogen were called Type 2, and those without hydrogen were called Type I. As observational techniques improved, finer distinctions were made, and Type 1 supernovas were subdivided into types Ia, Ib, and Ike. Type 2 supernovas, the core collapse supernovas we've been discussing, show strong hydrogen lines because the massive stars that explode retain their hydrogen-rich outer envelopes. These stars are so large and their outer layers so loosely bound that they don't lose much mass through stellar winds before they explode. When the shock wave from the core collapse reaches the surface and the star explodes, it blows off these hydrogen-rich layers, which produce the characteristic hydrogen emission lines in the spectrum. Type Ib and Ike supernovas, despite being classified as Type I based on their lack of hydrogen, are actually also core collapse supernovas. They come from massive stars that have lost their hydrogen envelopes before exploding. This can happen if the star has a very strong stellar wind that blows away the outer layers, or if the star is in a binary system and its companion strips away the hydrogen envelope. Type Ib supernovas show helium lines in their spectra, indicating that the star retained its helium layer even after losing its hydrogen. Type Ic supernovas lack even helium lines, suggesting that the progenitor star was stripped down to its core, composed mainly of carbon, oxygen, and heavier elements. But Type Ia supernovas are fundamentally different. They don't involve core collapse at all. Instead, they result from the thermonuclear explosion of a white dwarf star. White dwarfs are the remnants of low to medium mass stars with initial masses less than about 8 solar masses. These stars, which include our Sun, don't have enough mass to trigger core collapse. Instead, after billions of years of burning hydrogen and then helium, they shed their outer layers as a planetary nebula and leave behind their hot, dense cores, which become white dwarfs. A white dwarf is essentially a ball of carbon and oxygen, the ashes of helium burning, supported against gravity by electron degeneracy pressure. A solitary white dwarf will simply cool over billions of years, eventually becoming a cold, dark black dwarf. But if a white dwarf is in a close binary system with another star, it can have a very different fate. If the companion star is a normal star that evolves into a red giant, it may expand so much that its outer layers reach the white dwarf. The white dwarf's gravity pulls matter from the companion onto itself in a process called accretion. This matter, rich in hydrogen and helium, accumulates on the white dwarf's surface. As the white dwarf accretes more and more mass, its total mass increases. Remember the Chandrasekhar limit, approximately 1.4 solar masses, the maximum mass for a white dwarf. As the white dwarf's mass approaches this limit, the pressure and temperature at its center increase. Eventually, the central temperature becomes high enough for carbon fusion to ignite. But here's the key difference from normal stellar fusion. The white dwarf is supported by electron degeneracy pressure, not thermal pressure. In a normal star, if fusion suddenly releases extra energy, the star expands and cools, regulating the fusion rate. This is a negative feedback mechanism that keeps fusion under control. In a white dwarf, electron degeneracy pressure doesn't depend on temperature. If carbon fusion ignites, the extra energy doesn't cause expansion and cooling. Instead, It just makes the material hotter, which makes the fusion reactions proceed faster, which releases more energy, which makes it even hotter. This is a runaway process, a positive feedback loop that leads to a thermonuclear explosion. Within a few seconds, a substantial fraction of the white dwarf undergoes explosive fusion, converting carbon and oxygen into heavier elements, primarily silicon and iron peak elements like nickel and iron. The energy released, approximately 10 to the power of 44 joules, is enough to completely unbind the white dwarf. The entire star is blown apart in the explosion. Nothing is left behind. No neutron star, no black hole, just an expanding cloud of gas enriched with iron and other heavy elements. Type Ia. Supernovas are remarkably uniform in their properties because they all involve white dwarfs of approximately the same mass, right at the Chandrasekhar limit, undergoing the same runaway fusion process. This uniformity makes them incredibly useful to astronomers. Type Ia supernovas have a characteristic peak brightness, shining at approximately 5 billion times the sun's luminosity. By measuring how bright a Type Ia supernova appears and comparing it to its known intrinsic brightness, astronomers can determine how far away it is. This makes Type Ia supernovas standard candles for measuring cosmic distances. In the late 1992, two teams of astronomers used Type Ia supernovas to measure the expansion rate of the universe at different distances and therefore at different times in the past. They made a shocking discovery. The expansion of the universe is accelerating. Distant Type Ia supernovas were fainter than expected, indicating they were farther away than they should be in a universe expanding at a constant rate. This discovery provided the first direct evidence for dark energy, a mysterious component of the universe that exerts a kind of anti-gravity effect, causing the expansion to accelerate. Dark energy makes up about 68% of the total energy density of the universe, yet we don't know what it is. The discovery of cosmic acceleration through Type Ia supernova observations earned the Nobel Prize in Physics in 2011. An alternative scenario for producing Type Ia supernovas involves the merger of two white dwarfs. If two white dwarfs orbit each other closely enough, they emit gravitational waves and gradually spiral together. When they merge, their combined mass can exceed the Chandrasekhar limit, triggering a thermonuclear explosion. Recent observations suggest that both scenarios, single white dwarf secreting from companions and double white dwarf mergers, can produce Type Ia supernovas. There are even more exotic types of supernovas. Pair instability supernovas occur in extremely massive stars, those with initial masses above about 130 solar masses. In these stars, the core becomes so hot that high-energy gamma rays create electron-positron pairs. This process removes energy from the core, reducing pressure support. The core contracts, heats up further, and undergoes explosive oxygen and silicon burning. The explosion is so powerful that it completely destroys the star, leaving no remnant behind. Electron capture supernovas occur in stars of about 8 to 10 solar masses, right at the boundary between stars that become white dwarfs and stars that undergo core collapse. In these stars, the core is composed of oxygen, neon, and magnesium rather than iron. As the core contracts, electrons are captured by neon and magnesium nuclei, removing the electron degeneracy pressure that was supporting the core. The core collapses, but because these stars are not very massive, the resulting explosion is relatively weak. Hypernovas, also called supernovas, of type Ike-BL for broadline, are extremely energetic core collapse supernovas associated with long-duration gamma-ray bursts. These events involve the collapse of a rapidly rotating massive star, and they're thought to produce some of the most massive stellar black holes. Chapter 7: Supernova Remnants. The story doesn't end when the supernova fades. The expanding shell of material ejected in the explosion continues to interact with the surrounding interstellar medium for thousands of years, creating beautiful and complex structures called supernova remnants. As the supernova ejector races outward at thousands of kilometers per second, it plows into the surrounding gas and dust. The collision creates a strong shock wave that heats the gas to millions of degrees, causing it to emit X-rays. The shock also accelerates particles to extremely high energies, creating cosmic rays, high-energy protons, and atomic nuclei that zip through space at speeds approaching the speed of light. Young supernova remnants, less than a few thousand years old, show a shell-like structure. The bright shell marks the location of the shockwave, where the fast-moving ejector is colliding with the surrounding medium. Behind the shell, the material that has already been shocked cools and emits light at various wavelengths. One of the most famous supernova remnants is the Crab Nebula, the remnant of a supernova that exploded in the year 1054 AD. Chinese, Arabic, and Native American astronomers recorded the appearance of a brilliant guest star in the constellation Taurus. The supernova was visible in daylight for 23 days and remained visible at night for nearly 2 years. Today, we see an expanding, glowing cloud about 11 light-years across, still growing at 1,500 kilometers per second. At the heart of the Crab Nebula lies a pulsar, spinning 30 times per second, its powerful magnetic field and rapid rotation powering the nebula's glow. The pulsar generates a wind of high-energy particles that flows outward, creating a bubble of relativistic plasma within the supernova remnant. This pulsar wind nebula produces a ghostly blue glow in visible light images and shines brilliantly in X-rays. The Crab Nebula pulsar is one of the brightest pulsars in the sky and has been studied intensively since its discovery in 1968. Another spectacular supernova remnant is Cassiopeia A, the remnant of a supernova that exploded approximately 340 years ago, around 1680. Although the supernova should have been visible from Earth, no reliable historical records of it exist, possibly because interstellar dust dimmed the light. Cassiopeia A is currently about 10 light-years across and expanding at approximately 4,000 kilometers per second. X-ray observations of Cassiopeia A have revealed its complex structure in exquisite detail. The remnant shows bright knots of silicon-rich material, the products of explosive nucleosynthesis during the supernova. There's also a neutron star at the center, one of the youngest known neutron stars in our galaxy. Interestingly, this neutron star is unusually faint, suggesting it might have an atmosphere of carbon, making it one of the most exotic objects known. The Vela supernova remnant, the debris from a supernova that exploded approximately 11,000 years ago, is one of the closest supernova remnants to Earth, at a distance of about 800 light-years. It spans approximately 8 degrees across the sky, about 16 times the diameter of the full moon. The Vela remnant is so large and so close that it fills a substantial portion of the southern sky, though it's too faint to see with the naked eye. At the center of the Vela remnant is the Vela pulsar, rotating 11 times per second. This pulsar has been caught glitching, suddenly spinning faster for brief periods. These glitches are thought to occur when the superfluid interior of the neutron star suddenly transfers angular momentum to the crust, causing the star's rotation to speed up abruptly. Studying these glitches helps astronomers understand the exotic physics of neutron star interiors. The oldest visible supernova remnants are tens of thousands of years old and have expanded to diameters of hundreds of light years. By this time, the initial shock wave has weakened considerably, and the remnant is merging with the general interstellar medium. Eventually, after perhaps 100,000 years, the supernova remnant becomes indistinguishable from the surrounding gas, its energy fully dissipated, its material completely mixed with the interstellar medium. But the supernova's influence persists far longer. The heavy elements it scattered into space become part of the next generation of stars. The shock waves it sent through the interstellar medium may trigger the collapse of nearby gas clouds, initiating new star formation. The cosmic rays it accelerated continue racing through the galaxy for millions of years. Supernova remnants are also important sources of kinetic energy in the interstellar medium. The explosions stir up the gas, creating turbulence and preventing all of it from settling into a thin, calm disk. This turbulence affects star formation rates and the structure of galaxies. Computer simulations of galaxy evolution have shown that without energy input from supernovas, galaxies would look very different from what we observe. Too many stars would form too quickly, and galaxies would be denser and more compact than they actually are. Chapter 8: Observing Supernovas. For astronomers, catching a supernova as it explodes is like winning the lottery. Supernovas are rare events. In a typical galaxy like the Milky Way, a core collapse supernova occurs approximately once every 50 years on average, and a Type Ia supernova occurs approximately once every few hundred years. But galaxies are large, and most supernovas occur far from Earth, hidden by dust, or simply in directions we're not looking at the moment of explosion. Throughout recorded history, only a handful of supernovas in our galaxy have been visible to the naked eye. The supernova of 185 AD was recorded by Chinese astronomers. The supernova of 1006 AD was the brightest stellar event in recorded history, shining brightly enough to cast shadows at night and remaining visible for months. It was documented by observers in China, Japan, Europe, and the Arab world. The supernova of 1054 AD, which created the Crab Nebula, was also well documented. In 1572, the Danish astronomer Tycho Brahe observed a supernova in the constellation Cassiopeia. Tycho's supernova, as it's now called, was as bright as Venus and remained visible to the naked eye for 18 months. Tycho's careful observations of this new star challenged the Aristotelian view that the heavens were unchanging and eternal. This was revolutionary thinking in an era when the prevailing cosmology held that celestial objects were perfect and immutable. Just 32 years later, in 1604, another supernova appeared, this time in the constellation Ophiuchus. This supernova, known as Kepler's supernova after Johannes Kepler, who studied it extensively, was visible to the naked eye for a year. It was the last supernova in our galaxy that was visible without telescopes. Since then, no supernovas have been observed in the Milky Way, though several have likely occurred. The galaxy is large and contains substantial amounts of dust that blocks visible light, especially along the plane of the disk where most stars reside. A supernova could occur on the far side of the galaxy, and we might not see it at visible wavelengths. However, we could detect it in other wavelengths like radio or X-rays, or through its neutrinos. One supernova that astronomers dearly hope to observe is Betelgeuse. This red supergiant, one of the brightest stars in the night sky, is in the late stages of its life. At any time, it could explode as a supernova. At a distance of approximately 640 light-years, Betelgeuse is close enough that its supernova would be spectacular from Earth. It would likely shine as brightly as the full moon and be visible in daylight for weeks or months. However, any time in astronomical terms could mean tomorrow or 100,000 years from now. Betelgeuse has been observed to vary in brightness irregularly, and in late 2019 and early 2020, it dimmed dramatically, dropping to less than half its normal brightness. This sparked speculation that the star might be about to explode. However, subsequent observations showed that the dimming was caused by dust ejected from the star's surface, which temporarily blocked some of the light. Betelgeuse has since returned to its normal brightness. When Betelgeuse does eventually explode, it will be a magnificent sight and a scientific bonanza. Astronomers around the world have plans in place to observe the supernova across the electromagnetic spectrum, from radio waves to gamma rays. Neutrino detectors will record the burst of neutrinos from the core collapse, providing a direct probe of the explosion mechanism. The supernova will be studied in unprecedented detail and will learn an enormous amount about how massive stars die. Modern supernova searchers observe thousands of galaxies regularly, looking for new points of light that weren't there before. Automated telescopes can survey vast areas of sky each night, and computer algorithms compare new images with older ones to identify transient objects. When a potential supernova is found, follow-up observations with larger telescopes confirm its nature and study its properties. These surveys have been remarkably successful. Astronomers now discover hundreds of supernovas each year in galaxies near and far. Each discovery provides data about supernova properties, helping refine our models of stellar evolution and explosion mechanisms. One of the most important supernova discoveries in recent decades came in 1987, when a supernova exploded in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way located about 160,000 light-years away. Supernova 1987A, as it was designated, was the closest supernova observed since the invention of the telescope and the brightest supernova since Kepler's supernova in 1604. Supernova 1987A provided an unprecedented opportunity to study a supernova in detail. Astronomers observed it across the electromagnetic spectrum, from radio waves through optical light to gamma rays. They detected neutrinos from the core collapse, the first and so far only time neutrinos from a supernova have been directly observed. The neutrino detection came from 3 neutrino detectors: Kamiokande in Japan, IMB in the United States, and Baksan in Russia. Together, they detected about 24 neutrinos, arriving in a burst lasting about 13 seconds, approximately 3 hours before the supernova became visible. This neutrino detection confirmed a key prediction of supernova theory, that neutrinos carry away most of the energy from the core collapse and escape hours before the shockwave reaches the surface and the supernova brightens. The observation of neutrinos from supernova 1987A was such a significant achievement that it earned the 2002 Nobel Prize in Physics for Raymond Davis Jr. and Masatoshi Koshiba, whose detectors made the discovery possible. In the decades since 1987, astronomers have continued to monitor the expanding remnant of supernova 1987A. As the blast wave from the explosion has expanded, it has collided with material ejected by the progenitor star before it exploded. This collision has created bright rings of glowing gas that are expanding and evolving. Observations with the Hubble Space Telescope and other instruments have tracked these changes, providing insights into the final stages of the progenitor star's life and the structure of the material surrounding it. Interestingly, despite extensive searches, Astronomers have not yet definitively detected the neutron star or black hole that should have formed when supernova 1987A's core collapsed. There are hints of a compact object at the center of the expanding remnant, but it hasn't been conclusively identified. The object might be shrouded in dense dust created in the explosion, or it might be an unusually faint neutron star. Alternatively, if the core was massive enough, it might have collapsed directly to a black hole, which would be much harder to detect. Chapter 9. The role of supernovas in the cosmos. Supernovas are not just spectacular events to observe. They play crucial roles in the evolution of galaxies, the chemical enrichment of the universe, and possibly even the origin of life. We've already discussed how supernovas create and distribute heavy elements, but let's put this in perspective. In the early universe, just a few minutes after the Big Bang, only the lightest elements existed: hydrogen, helium, and trace amounts of lithium and beryllium. Everything heavier, from carbon to uranium, had to be created in stars or stellar explosions. The first stars, formed a few 100 million years after the Big Bang, contained no heavy elements. They were composed almost entirely of primordial hydrogen and helium. These first-generation stars are called population 3 stars, and none have been directly observed because they all died billions of years ago. But theoretical models suggest they were extremely massive, hundreds of times the mass of the Sun, and they lived fast and died young, exploding as supernovas after just a few million years. The supernovas of these first stars scattered the first heavy elements into space. Subsequent generations of stars formed from gas enriched with these elements, and each generation added more. Our Sun is a relatively late generation star, formed about 4.5 billion years ago from gas that had been enriched by billions of years of stellar evolution. The heavy elements in the Sun and in the planets that formed around it are the accumulated products of countless stars that lived and died over the first 9 billion years of cosmic history. Without supernovas, there would be no heavy elements. Without heavy elements, there could be no rocky planets like Earth. Without rocky planets, there could be no life as we know it. Every atom of oxygen in the water you drink, every atom of calcium in your bones, every atom of iron in your blood was created inside a star and scattered into space by a supernova billions of years ago. You are quite literally made of stardust, the debris of stellar explosions. Supernovas also trigger star formation. The shock waves from supernova explosions compress nearby clouds of gas and dust, and if the compression is strong enough, it can trigger gravitational collapse and the formation of new stars. Some of the most active star-forming regions in our galaxy, such as the Orion Nebula, show evidence of having been triggered by shock waves from supernovas or stellar winds from massive stars. There's even speculation that a supernova might have triggered the formation of our solar system. Some meteorites contain isotopes, such as iron 60, that are produced in supernovas and decay relatively quickly on geological timescales. The presence of these short-lived isotopes in the oldest meteorites suggests that a supernova exploded near the cloud of gas from which the solar system formed just before or during the collapse that created the Sunday. The shock wave from this supernova might have triggered the collapse, making that long-dead star indirectly responsible for our existence. Supernovas also affect life in more direct ways, though these effects are controversial and not fully understood. Cosmic rays, high-energy particles accelerated by supernova shock waves, constantly rain down on Earth. When cosmic rays strike molecules in Earth's upper atmosphere, they create showers of secondary particles, including muons that reach the surface. These particles can damage DNA and cause mutations. For most of Earth's history, the mutation rate caused by cosmic rays has been relatively constant and low. Evolution has adapted to this background level of mutations, and in fact, mutations are essential for evolution, providing the variation on which natural selection acts. But if a nearby supernova occurred, the flux of cosmic rays reaching Earth could increase dramatically for a period of years or decades. Some researchers have proposed that mass extinctions in Earth's history might have been caused or triggered by nearby supernovas. The idea is that increased cosmic ray flux would damage the ozone layer, allowing more ultraviolet radiation from the sun to reach Earth's surface. UV radiation is harmful to many forms of life, particularly small organisms and the larval stages of many species. A prolonged period of elevated UV radiation could cause widespread extinctions. Evidence for this idea is mixed and controversial. Some studies have found correlations between extinction events and supernova activity, while others have not. It's also worth noting that supernovas are rare, and very close supernovas, within about 30 light-years of Earth, are extremely rare. The last supernova close enough to have had significant effects on Earth probably occurred millions of years ago. On the positive side, the enhanced mutation rate from cosmic rays might occasionally spur evolutionary innovation. Mutations are the raw material of evolution, and periods of increased mutation rate could lead to rapid evolutionary change. Some researchers have speculated that the diversification of life at certain points in Earth's history might have been influenced by nearby supernovas, though this remains highly speculative. Supernovas also affect the evolution of galaxies as a whole. The energy they inject into the interstellar medium creates hot bubbles of gas that expand and merge, forming a complex network of cavities and shells. This structure affects how gas cools and collapses to form new stars. Simulations of galaxy evolution show that without the energy input from supernovas, star formation would proceed much faster, and galaxies would be denser and have different structures than observed. In the largest galaxies, supermassive black holes at the galactic centers also inject energy into the surrounding gas, regulating star formation. But in smaller galaxies, supernovas are the dominant source of feedback. Understanding how supernovas affect galaxy evolution is an active area of research, with implications for understanding galaxy formation and the history of star formation throughout cosmic time. Chapter 10: Extreme Supernovas and Exotic Outcomes. While most supernovas follow the patterns we've described, nature occasionally produces explosions that are far more extreme. These exotic events probe the limits of stellar physics and create some of the most enigmatic objects in the universe. Hypernovas, also called collapsars, are core collapse supernovas with kinetic energies 10 to 100 times higher than typical supernovas. Instead of releasing 10 to the power of 44 joules of kinetic energy, hypernovas release 10 to the power of 45, or even 10 to the power of 46 joules. These explosions are so powerful that they briefly outshine entire galaxy clusters. Hypernovas are associated with long-duration gamma-ray bursts, the most energetic explosions in the universe, apart from the Big Bang itself. Gamma-ray bursts come in two types: short bursts lasting less than 2 seconds, and long bursts lasting more than 2 seconds. Long-duration gamma-ray bursts are produced by hypernovas, the collapse of rapidly rotating massive stars. The current model for long gamma-ray bursts involves a massive star, at least 25 to 30 times the mass of the Sun, that is rotating rapidly. When the core collapses, it forms a black hole, but the rotation prevents some of the infalling material from reaching the black hole immediately. Instead, this material forms an accretion disk around the black hole. The accretion disk is incredibly hot and dense, and powerful magnetic fields thread through it. These magnetic fields can launch jets of material along the rotation axis of the black hole at speeds approaching the speed of light. These jets punch through the outer layers of the star and break free into space, carrying enormous amounts of energy. The gamma-ray burst itself is produced when the jets interact with material outside the star, converting their kinetic energy into gamma rays through various mechanisms. The burst is highly beamed, meaning it's only visible if you're looking nearly along the jet axis. If you're off to the side, you see only the supernova itself, which appears as a typic supernova with unusually high energy. Because gamma-ray bursts are beamed, we only see a small fraction of them, those whose jets happen to be pointed toward Earth. This means that hypernovas might be more common than gamma-ray burst observations alone would suggest. Every long-duration gamma-ray burst has an associated hypernova, but not every hypernova produces a gamma-ray burst we can detect. The most luminous gamma-ray burst ever observed, GRB 080916c, released more energy in a few minutes than the Sun will emit in its entire 10 billion year lifetime. At its peak, this burst was briefly the most luminous object in the universe. The progenitor star must have been extraordinary, perhaps a star 100 times the mass of the Sun, rotating at a substantial fraction of its breakup speed. Pair instability supernovas represent another extreme. These occur in extremely massive stars, those with initial masses between about 130 and 250 solar masses. Such massive stars probably existed in the early universe, when gas clouds had lower metallicity and could collapse to form more massive stars than today. In the cores of these extremely massive stars, temperatures reach several billion degrees. At these temperatures, thermal photons, the gamma rays bouncing around in the core, have enough energy to spontaneously create electron-positron pairs. This process, called pair production, removes energy from the radiation field, reducing the radiation pressure that helps support the core. As the pressure drops, the core contracts and heats up, which should increase the pressure and restore equilibrium. But at the temperatures where pair production is important, this doesn't happen. Instead, the increased temperature leads to more pair production, which removes even more energy. The core becomes unstable and collapses. The collapse triggers explosive oxygen and silicon burning throughout the core. The entire star is disrupted in a thermonuclear explosion so powerful that it completely destroys the star, leaving no remnant behind. The explosion energy can reach 10 to the power of 45 joules, and the star becomes as luminous as an entire galaxy for weeks. Pair instability supernovas are thought to produce large amounts of iron peak elements, including radioactive nickel 5-6, which decays to cobalt 5-6 and then to stable iron 5-6. The decay of nickel 5-6 powers the light curve of the supernova, causing it to remain bright for an extended period. Observations have identified a few candidates for pair instability supernovas, but confirmed examples remain rare. At the other extreme are electron capture supernovas, which occur in stars just barely massive enough to avoid becoming white dwarfs. In these stars, the core is composed primarily of oxygen, neon, and magnesium. As the core contracts after burning its outer layers, electrons in the core are captured by neon and magnesium nuclei, converting them to sodium and oxygen, respectively, and producing neutrinos. This electron capture removes electrons from the core, reducing the electron degeneracy pressure that's supporting it. The core collapses, but because these stars are relatively low mass, the collapse produces a much weaker explosion than typical core collapse supernovas. The explosion energy might be only 10 to the power of 43 joules, a tenth of a normal supernova. Electron capture supernovas are interesting because they occur in stars that wouldn't normally be massive enough for core collapse. They fill a gap in the mass spectrum between stars that become white dwarfs and stars that undergo normal core collapse supernovas. Recent observations suggest that some unusually faint supernovas might be electron capture events, but confirming this requires detailed modeling of the explosions and their light curves. Failed supernovas represent perhaps the most intriguing extreme case. Computer simulations suggest that in some massive stars, particularly those with initial masses between about 20 and 30 solar masses, the core collapse might not produce a successful explosion. The shock wave stalls and cannot be revived, and the outer layers of the star fall back onto the newly formed neutron star or black hole. From the outside, a failed supernova might produce only a brief, faint optical transient as the outer layers fall back, or it might be completely invisible. The star simply disappears, collapsing into a black hole without the spectacular fireworks of a normal supernova. Observations over the past decade have found a few cases where massive stars seem to have vanished without exploding, consistent with failed supernovas. Though alternative explanations exist, failed supernovas have important implications for our understanding of black hole formation. If a significant fraction of massive stars collapse directly to black holes without exploding, this affects estimates of supernova rates, heavy element production, and energy injection into galaxies. It also affects the mass distribution of stellar black holes. Stars that undergo failed supernovas produce more massive black holes because more of the star's mass falls back onto the core. Chapter 11: Supernovas and the Expanding Universe. Type Ia supernovas, the thermonuclear explosions of white dwarfs, have played a crucial role in one of the most important astronomical discoveries of the past few decades: the accelerating expansion of the universe. In the 1,990 seconds, two teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, set out to use Type Ia supernovas to measure the expansion history of the universe. Their goal was to determine whether the universe's expansion was slowing down due to gravity, as most cosmologists expected, and to measure how quickly it was decelerating. Type Ia supernovas are ideal for this purpose because they're bright enough to be seen across billions of light years and they have a consistent peak luminosity. This makes them standard candles, objects whose intrinsic brightness is known, allowing astronomers to determine their distance by measuring how bright they appear. The strategy was straightforward. Observe Type Ia supernovas at various distances, measure their redshifts to determine how fast they're receding due to cosmic expansion, and measure their apparent brightness to determine their distances. By comparing the relationship between distance and recession, velocity for nearby and distant supernovas, the teams could reconstruct the expansion history of the universe. Both teams expected to find that the expansion was slowing down. The universe contains matter, and matter's gravity should pull back on the expansion, causing it to decelerate over time. The question was how much deceleration was occurring, which would reveal how much matter the universe contains. But when the teams analyzed their data in 1998, they found something completely unexpected. Distant supernovas were fainter than expected, indicating they were farther away than they should be in a decelerating universe. Instead of slowing down, the universe's expansion was speeding up. This discovery was so surprising that both teams initially questioned their results. They checked for every possible source of error: dust between us and the supernovas that might make them appear fainter, evolution in supernova properties over cosmic time that might make distant supernovas intrinsically dimmer, selection biases in their samples. But no matter how carefully they checked, the conclusion remained the same. The universe's expansion is accelerating. An accelerating expansion requires something with repulsive gravity, something that pushes space apart rather than pulling matter together. Astronomers call this dark energy, and it's one of the deepest mysteries in physics. Dark energy makes up approximately 68% of the total energy density of the universe, yet we don't know what it is. The simplest explanation for dark energy is that it's a cosmological constant, a uniform energy density inherent to space itself. Einstein introduced the cosmological constant in 1917, adding it to his equations of general relativity to allow for a static universe, which was the prevailing belief at the time. When Hubble discovered that the universe is expanding in 1929, Einstein reportedly called the cosmological constant his biggest blunder and removed it from his equations. But the supernova observations brought the cosmological constant back. If space itself has a uniform energy density, this energy would exert a kind of negative pressure, causing space to expand faster and faster. The more space exists, the more dark energy there is, and the faster the expansion proceeds. This creates an accelerating expansion exactly like what the supernova observations showed. Alternative explanations for dark energy involve new fields or modifications to general relativity, but so far, observations are consistent with a simple cosmological constant. The nature of dark energy remains one of the most important unsolved problems in physics, with implications for the ultimate fate of the universe. For their discovery of cosmic acceleration through supernova observations, Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics. Their work transformed our understanding of the universe's composition and evolution, revealing that ordinary matter and dark matter together make up only about 32% of the universe's total energy content. The discovery also has implications for the far future. An accelerating expansion means that the universe will continue expanding forever, and the expansion will get faster and faster. Eventually, billions of years from now, distant galaxies will be receding so fast that their light can no longer reach us. The observable universe will shrink, not because space is contracting, but because the accelerating expansion carries distant objects beyond our cosmic horizon. In the very far future, trillions of years from now, our local group of galaxies will be the only galaxies we can see. Everything else will have been carried away by the expansion. Stars will exhaust their fuel, galaxies will grow dark, and the universe will become cold, dark, and empty. This scenario, called the heat death or big freeze, is the most likely fate of our universe based on current observations, but that's trillions of years away. For now, we live in a vibrant era, a cosmic golden age when the universe is filled with shining stars and spectacular supernovas, and we're fortunate enough to witness and study them. Chapter 12: The Future of Supernova Research. Our understanding of supernovas has advanced enormously over the past century, but many questions remain. The next generation of telescopes and detectors promises to revolutionize supernova astronomy and answer long-standing mysteries. One of the most exciting developments is the construction of large survey telescopes designed to monitor the entire visible sky every few nights. The Vera C. Rubin Observatory, scheduled to begin operations in the mid-2022, will use a 8.4-meter telescope with an enormous camera to photograph the entire southern sky every 3 nights. This legacy survey of space and time will discover thousands of supernovas, including rare and unusual types that current surveys might miss. The Rubin Observatory will detect supernovas at the moment of explosion, catching the first light as the shockwave breaks through the star's surface. These early observations are crucial for understanding the explosion mechanism and the structure of the progenitor star. Current surveys often discover supernovas days or weeks after explosion, missing this critical early phase. Multi-messenger astronomy, combining observations of light, gravitational waves, and neutrinos from the same event, is another frontier. The detection of neutrinos from the next galactic supernova will provide unprecedented insights into the core collapse process. Several neutrino detectors around the world, including IceCube at the South Pole, Super Kamiokande in Japan, and DUNY in the United States, are constantly monitoring for neutrino bursts. When the next galactic supernova occurs, these detectors will record thousands of neutrinos, vastly more than the 24 detected from supernova 1987A. The neutrino signal will reveal details of the core collapse, including the mass of the collapsing core, whether a neutron star or black hole forms, and possibly even the equation of state of nuclear matter at extreme densities. Gravitational wave detectors are also being prepared for supernova observations. While gravitational waves from supernovas are much weaker than those from binary black hole mergers, a sufficiently close supernova could be detected. The gravitational wave signal would reveal asymmetries in the explosion, the rotation rate of the collapsing core, and potentially the formation of a rotating neutron star. Advances in computer simulations are also pushing the boundaries of our understanding. Modern supercomputers can now simulate core collapse supernovas in 3 dimensions, including detailed physics of neutrino transport, nuclear reactions, magnetic fields, and general relativistic effects. These simulations have shown that supernova explosions are inherently 3-dimensional and asymmetric, with complex flows and instabilities playing crucial roles. Recent simulations have achieved successful explosions for a range of progenitor masses without artificially boosting the energy. This represents a major breakthrough, as previous simulations often failed to produce explosions or required artificial adjustments. The success of these simulations validates our basic understanding of the explosion mechanism, while revealing new complexities. One persistent mystery is the red supergiant problem. Observations show that most supernova progenitors are red supergiants, as expected, but there's a curious lack of progenitors more massive than about 18 solar masses. Stars more massive than this should also explode as supernovas, so why don't we see them? Several explanations have been proposed. Maybe very massive stars lose most of their mass through stellar winds before exploding, making them appear less massive than they actually were when born. Maybe some massive stars collapse directly to black holes without bright explosions as failed supernovas. Or maybe there's something wrong with our models of stellar evolution for very massive stars. Resolving this mystery requires better observations of supernova progenitors. With modern surveys monitoring millions of stars, we can identify more progenitors by comparing pre-explosion images with the locations of newly discovered supernovas. Each progenitor detection provides clues about which types of stars explode and how. Another area of active research involves superluminous supernovas, explosions that are 10 to 100 times brighter than normal supernovas. These ultra-bright events were first discovered in the 2000s and remain poorly understood. Some might be pair instability supernovas, while others might involve interactions between the expanding supernova ejecta and dense material surrounding the star. One class of superluminous supernovas shows strong hydrogen lines, suggesting the progenitor star was surrounded by a thick shell of hydrogen-rich material. When the supernova ejecta slam into this shell, The collision converts kinetic energy into light, making the supernova appear much brighter than normal. These interaction-powered supernovas can remain bright for months or even years as the ejecta plow through the surrounding material. Other superluminous supernovas lack hydrogen and might be powered by the spin-down of a rapidly rotating neutron star called a magnetar. If the core collapse produces a neutron star with an extremely strong magnetic field and rapid rotation, the magnetic dipole radiation from the neutron star can inject enormous amounts of energy into the expanding ejecta, powering a bright display. Over weeks to months, the neutron star spins down, transferring its rotational energy to the supernova light. Understanding superluminous supernovas is important because they might be the modern analogues of the first supernovas in the universe. The first stars, formed from primordial gas with no heavy elements, were probably very massive and might have exploded as superluminous supernovas. Studying nearby superluminous supernovas helps us understand what these first explosions were like and how they enriched the early universe with heavy elements. Chapter 13: Supernovas and the Search for Life. The connection between supernovas and life extends beyond the creation of heavy elements. Supernovas might influence the habitability of planets and even the distribution of life in the galaxy. Earth exists in what astronomers call the galactic habitable zone, a region of the Milky Way where conditions are favorable for life. Too close to the galactic center, and the density of stars is high, making close encounters and supernova explosions more frequent. Too far from the center, and there aren't enough heavy elements to form rocky planets. Earth orbits about 26,000 light-years from the galactic center, in a relatively quiet region with modest supernova rates and sufficient heavy element abundance. This location might not be coincidental. Regions with higher supernova rates might be too hazardous for complex life to develop and persist over billions of years. The radiation from a nearby supernova could damage Earth's ozone layer, allowing harmful ultraviolet radiation from the Sun to reach the surface. Studies suggest that a supernova within about 25 light-years of Earth could cause significant ozone depletion. Fortunately, there are no massive stars likely to explode as supernovas within this distance in the near future. However, over Earth's 4.5 billion-year history, several nearby supernovas have probably occurred. Some researchers have proposed connections between supernova events and mass extinctions, though evidence remains inconclusive. The extinction at the end of the Devonian period, about 375 million years ago, has been speculatively linked to a nearby supernova based on the presence of certain isotopes in rocks from that time. More controversially, some scientists have suggested that nearby supernovas might have influenced human evolution. The idea is that increased cosmic ray flux from a nearby supernova a few million years ago might have increased mutation rates, potentially contributing to the rapid evolutionary changes that led to modern humans. This hypothesis is highly speculative and difficult to test, but it illustrates how supernovas might have indirect effects on life. On the positive side, supernovas make life possible by creating heavy elements. Without the carbon, oxygen, and other elements produced in stars and scattered by supernovas, there could be no organic chemistry, no water, no rocky planets. Life as we know it is built from supernova debris. This raises interesting questions about life elsewhere in the universe. Planets around the first generation of stars, those formed before any supernovas had occurred, could not support life as we know it. They lacked the heavy elements necessary for chemistry, oceans, and solid surfaces. Life could only begin appearing in the universe after enough supernovas had enriched the interstellar medium with heavy elements. This means there's a minimum age for habitable planets in the universe. The first stars formed a few 100 million years after the Big Bang, and they lived and died over the next few 100 million years. But it probably took several generations of stars, several billion years of cosmic chemical enrichment before planets like Earth could form. Life-bearing planets probably couldn't exist much before about 8 or 9 billion years after the Big Bang. Our solar system formed about 9 billion years after the Big Bang, relatively late in cosmic history. This timing might be significant. If complex life requires billions of years to evolve, as it did on Earth, then the universe needed to be old enough not just for life to start, but for it to develop into complex, technological civilizations. We might be among the earlier technological civilizations in the universe, or we might be typical. We simply don't know. The search for extraterrestrial intelligence, or SETI, sometimes considers supernova rates when identifying promising target stars for observation. Stars in regions with very high supernova rates might be less likely to harbor long-lived civilizations. On the other hand, a civilization that survives in such an environment might develop robust technology for detecting and possibly protecting against supernova effects. Some scientists have even speculated about using supernovas as beacons for interstellar communication. A sufficiently advanced civilization might be able to trigger a supernova artificially, or at least predict when one is about to occur naturally, and use it to send signals across the galaxy. The immense energy of a supernova could potentially be modulated to encode information visible to anyone watching. This is purely speculative, of course, but it illustrates how supernovas connect to even the most imaginative questions about life in the cosmos. Chapter 14. Personal stories from supernova hunters. Behind the dry scientific papers and technical observations are human stories of dedication, discovery, and occasionally pure luck. Supernova astronomy has been shaped by countless individuals whose passion drove them to spend cold nights at telescopes, countless hours analyzing data, and years waiting for that one spectacular event. Fritz Zwicky, the Swiss-American astronomer working at Caltech in the 1930 seconds, coined the term supernova to distinguish these brilliant stellar explosions from ordinary novae, which are much less energetic events involving white dwarfs accreting matter from companions. Zwicky was extraordinarily productive, discovering over 100 supernovas personally using relatively small telescopes. He developed systematic search techniques, photographing the same galaxies repeatedly and comparing images to find new stars. Zwicky was also famously difficult to work with, often calling his colleagues spherical bastards because, as he put it, they were bastards no matter which direction you looked at them. Despite his abrasive personality, his contributions to astronomy were immense. He was among the first to propose that supernovas could produce neutron stars, an idea that seemed outlandish in the 1930 seconds, but was later confirmed. He also pioneered the study of dark matter, though his work in this area was largely ignored during his lifetime. Robert Evans, an amateur astronomer and minister in Australia, holds the record for visual supernova discoveries, having found 42 supernovas by visually comparing the appearance of galaxies through his backyard telescope with his memory of how they should look. Evans developed an extraordinary ability to memorize the appearance of thousands of galaxies, allowing him to immediately recognize when something new appeared. In an era before automated surveys, Evans's discoveries were remarkable achievements, requiring patience, dedication, and an exceptional memory. The discovery of supernova 1987A was made by Ian Shelton, a Canadian astronomer working at Las Campanas Observatory in Chile, and Oscar Duhalde, a telescope operator at the same facility. On the night of the 23rd of February 1987, Shelton was photographing the Large Magellanic Cloud, a nearby satellite galaxy visible from the southern hemisphere. When he developed his photographic plate, he noticed a bright star that hadn't been there on previous images. He rushed outside to confirm that it was visible to the naked eye, and indeed, there was a new bright star in the Large Magellanic Cloud. Almost simultaneously, Duhalde had spotted the supernova visually while outside during a break. Neither man initially realized they had discovered the closest supernova in nearly 400 years. Within hours, astronomers around the world were training their telescopes on supernova 1987, beginning what would become one of the most intensively studied objects in astronomical history. The neutrino detection from supernova 1987A was equally remarkable. The Kamiokande detector in Japan, originally built to search for proton decay, detected 11 neutrinos in a burst lasting about 13 seconds. The IMB detector in the United States detected 8 neutrinos. These detections were not immediately recognized as coming from a supernova. It was only after Shelton announced his discovery that physicists checked their data and realized they had detected the neutrino burst from the core collapse hours before the supernova became visible. This sequence of events, neutrinos first, then visible light, perfectly matched theoretical predictions. The neutrinos escaped from the collapsing core almost immediately, while the shock wave took hours to reach the star's surface. The time delay between the neutrino burst and the optical brightening allowed astronomers to determine that neutrinos travel at essentially the speed of light, or at least extraordinarily close to it, placing tight constraints on the neutrino mass. More recently, the search for supernovas has become increasingly automated. Dedicated survey telescopes patrol the sky nightly, and computer algorithms analyze the images, flagging potential supernovas for follow-up observation. The Zwicky Transient Facility, operating at Palomar Observatory in California, surveys the entire northern sky every 2 nights, discovering hundreds of supernovas per year, along with many other transient objects. Despite automation, human astronomers remain essential, following up on supernova discoveries, obtaining spectra to determine their types and distances, and conducting detailed observations at multiple wavelengths, all require human expertise and decision-making. The field has evolved from individual observers making lucky discoveries to coordinated international efforts involving hundreds of scientists, but the fundamental goal remains the same: understanding these spectacular cosmic events. Chapter 15: Supernovas in Other Galaxies. While supernovas in our own galaxy are rare and difficult to observe due to dust obscuration, supernovas in other galaxies are discovered regularly. Each discovery adds to our understanding of stellar evolution, explosion mechanisms, and cosmic chemical enrichment. The Andromeda Galaxy, our nearest large galactic neighbor at a distance of about 2.5 million light-years, experiences supernovas at a rate similar to the Milky Way, perhaps 1 or 2 per century. However, we can observe the entire galaxy from outside, unlike our own galaxy, where dust blocks much of our view. Several supernovas have been discovered in Andromeda over the past century, each providing an opportunity to study these events in a galaxy with properties similar to our own. More distant galaxies offer different perspectives. Supernovas in galaxies billions of light-years away show us how stellar explosions occurred in the distant past, when the universe was younger and galaxies had different properties. The composition of stars in the early universe differed from today, with lower abundances of heavy elements. This affects how stars evolve and explode. Population 3 stars, the first generation formed from primordial gas, contained virtually no heavy elements. These stars were probably very massive, and their supernovas would have been the first to enrich the universe with heavy elements. While no population 3 supernovas have been directly observed, they would have been extremely luminous and might be detectable with future telescopes. The James Webb Space Telescope, launched in December 2021, is specifically designed to observe the earliest stars and galaxies. While it hasn't yet detected population 3 supernovas, it has the capability to observe these events if they occur within its field of view. Alternatively, JWST might detect supernova remnants from population 3 explosions, providing indirect evidence of these first stellar deaths. Galaxy clusters, which can contain hundreds or thousands of galaxies, are excellent laboratories for supernova studies. The high galaxy density means supernovas occur frequently somewhere in the cluster. By monitoring clusters, astronomers can discover many supernovas and study how supernova rates and properties vary with galaxy type, size, and environment. Interestingly, supernova rates correlate with galaxy properties. Galaxies actively forming stars have higher supernova rates because massive stars, which produce core collapse supernovas, have short lifetimes. Elliptical galaxies, which have little ongoing star formation, experience mostly Type Ia supernovas from old white dwarfs. Spiral galaxies like the Milky Way have both types, with Type Ia supernovas occurring in the old stellar population and core collapse supernovas occurring in star-forming regions. The study of supernovas in other galaxies also helps calibrate cosmic distance measurements. Type Ia supernovas, as we've discussed, are standard candles used to measure distances across the universe. By observing Type Ia supernovas in galaxies whose distances are known through other methods, astronomers can calibrate the absolute brightness of Type Ia supernovas and improve distance measurements to more distant objects. This cosmic distance ladder, built from multiple measurement techniques that overlap in distance range, extends from parallax measurements of nearby stars through Cepheid variable stars to Type Ia supernovas, and finally to the cosmic microwave background radiation. Each rung must be carefully calibrated, and uncertainties at any level propagate to all subsequent measurements. Improving our understanding of Type Ia supernovas directly improves our knowledge of cosmic distances and the expansion rate of the universe. Chapter 16: The Physics of Neutron Stars. When a massive star's core collapses and forms a neutron star, the result is one of the most extreme objects in the universe. Understanding neutron stars requires pushing physics to its limits and beyond, into regimes that cannot be replicated in any laboratory on Earth. A neutron star is essentially an atomic nucleus the size of a city. The density at its center exceeds nuclear density, the density inside protons and neutrons, by several times. At such extreme densities, matter behaves in ways that are still not fully understood. The surface of a neutron star is thought to be solid, a crystal lattice of iron nuclei with a sea of electrons flowing through it. But this is no ordinary solid. The density at the surface is approximately 1 million times that of white dwarf material, itself about 1 million times denser than water. Moving inward, the density increases, and the nuclei become increasingly neutron-rich. At a depth of a few hundred meters, the nuclei become so neutron-rich that neutrons begin to drip out, forming a sea of free neutrons in addition to the lattice of nuclei. This inner crust is a bizarre state of matter with no earthly analogue, a crystal of exotic nuclei swimming in a neutron sea. Deeper still, the nuclei dissolve entirely into a neutron liquid. This neutron liquid is thought to be a superfluid, a quantum fluid with zero viscosity that can flow without friction. Superfluidity is a quantum phenomenon usually observed at temperatures near absolute zero in liquid helium. In a neutron star, superfluidity occurs despite temperatures of millions of degrees because the densities are so extreme that quantum effects dominate. The neutrons in this superfluid might also form Cooper pairs, bound states of two neutrons, creating a superfluid analogous to the superconducting state in metals. If this occurs, the neutron star's interior would be both superfluid and superconducting, with profound implications for the star's magnetic field evolution and heat transport. At the very center of the most massive neutron stars, densities might exceed the density at which neutrons themselves break down into their constituent quarks. Quarks are the fundamental particles that make up protons and neutrons. Normally, quarks are permanently confined inside protons and neutrons by the strong nuclear force. But at extremely high densities, this confinement might break down, creating quark matter. If quark matter exists in neutron star cores, these objects should more properly be called quark stars or hybrid stars, with a quark matter core surrounded by normal neutron matter. The transition from neutron matter to quark matter would occur at a specific density, creating a phase boundary inside the star. Detecting evidence for this phase transition is one of the goals of current neutron star research. The equation of state, the relationship between pressure and density, determines a neutron star's structure, maximum mass, and many observable properties. Unfortunately, the equation of state at densities exceeding nuclear density is poorly known. Nuclear physics experiments can probe the properties of nuclear matter at and somewhat above nuclear density, but the conditions inside neutron stars exceed what can be achieved in laboratories. This means that neutron star observations can constrain nuclear physics in ways that laboratory experiments cannot. By measuring neutron star masses and radii, astronomers can infer the equation of state and learn about the behavior of matter at extreme densities. Recent observations have made significant progress in this area. The NICER Neutron Star Interior Composition Explorer mission, mounted on the International Space Station, has measured the masses and radii of several pulsars with unprecedented precision. These measurements indicate that neutron stars have radii of approximately 12 to 13 kilometers for masses around 1.4 solar masses. This constrains the equation of state and suggests that matter remains relatively stiff, not easily compressed, even at these extreme densities. Gravitational wave observations of neutron star mergers provide complementary constraints. In August 2017, LIGO and Virgo detected gravitational waves from the merger of two neutron stars, an event designated GW170817. This merger was also observed across the electromagnetic spectrum, from gamma rays to radio waves, making it the first multi-messenger observation of a neutron star merger. The gravitational wave signal from GW170817 contained information about the neutron stars' masses and their deformability, how much they were distorted by each other's gravity as they spiraled together. This deformability depends on the equation of state. Stiff equations of state, where matter strongly resists compression, produce larger, more deformable neutron stars. Soft equations of state produce smaller, less deformable stars. The observations indicated that the equation of state is moderately stiff, consistent with the NICER measurements. Combined with mass measurements from binary pulsars and other sources, these constraints are beginning to pin down the properties of ultra-dense matter. Neutron stars also possess extraordinarily strong magnetic fields. A typical neutron star has a surface magnetic field about 1 trillion times stronger than Earth's magnetic field. But some neutron stars, called magnetars, have fields 1,000 times stronger still, approaching 10 to the power of 15 Gauss. These are the strongest magnetic fields known in the universe. The physics of magnetars is exotic. The magnetic field energy density exceeds the mass energy density of matter, meaning the magnetic field dominates the star's structure. The intense magnetic field stresses the neutron star's crust, occasionally causing it to crack in starquakes that release enormous amounts of energy in brief bursts of X-rays and gamma rays. The origin of magnetar fields remains debated. They might arise from amplification of the magnetic field during core collapse, particularly if the progenitor star was rapidly rotating. Alternatively, they might result from a dynamo process in the newly formed neutron star, where convection and differential rotation generate magnetic fields shortly after birth. Chapter 17. The Cosmic Recycling System. Supernovas are not endpoints, but waypoints in the cosmic cycle of matter and energy. The material they eject doesn't simply disperse into empty space. It interacts with the interstellar medium, enriching it, stirring it, and eventually being incorporated into new stars and planets. The interstellar medium, the gas and dust between stars, has a complex structure shaped by stellar winds, supernova explosions, and other energetic processes. In the densest regions, molecular clouds, gas is cold, dense, and shielded from starlight. These are the sites where new stars form. In the most diffuse regions, the hot ionized medium, gas is heated to millions of degrees by supernova shocks. When a supernova explodes, it injects energy and momentum into the surrounding medium. The expanding supernova remnant sweeps up interstellar gas, creating a shell of compressed material. This compression can trigger the gravitational collapse of nearby molecular clouds, initiating new star formation. Thus, supernovas beget stars, and those stars, if massive enough, will eventually explode as supernovas themselves. Continuing the cycle, this cycle operates on timescales of millions to billions of years. A molecular cloud collapses to form a cluster of stars. The most massive stars in the cluster live for just a few million years before exploding as supernovas. These explosions compress surrounding gas, triggering the formation of the next generation of stars. Meanwhile, the heavy elements produced in the supernovas mix with the interstellar gas, enriching it. Over cosmic time, this process gradually increases the metallicity, the fraction of heavy elements, in galaxies. The earliest galaxies, formed from primordial gas, had essentially zero metallicity. Each generation of stars increased the metallicity slightly. Today, different parts of galaxies show different metallicities, reflecting their star formation histories. In the Milky Way, metallicity generally decreases with distance from the galactic plane. Stars in the disk, where active star formation continues, have relatively high metallicity, similar to the Sunday. Stars in the halo, the spherical distribution of old stars surrounding the galaxy, have much lower metallicity because they formed early in the galaxy's history before much chemical enrichment had occurred. Individual stars carry records of the gas from which they formed. By measuring a star's chemical composition, astronomers can infer when and where it formed. Stars with very low metallicity, found occasionally in the galactic halo, formed early in cosmic history. Stars with high metallicity, particularly with enhanced abundances of elements like europium that are produced primarily in neutron star mergers, might have formed from gas enriched by a nearby merger event. The solar system's composition reflects approximately 9 billion years of galactic chemical evolution. The Sun contains about 2% heavy elements by mass, accumulated from countless generations of stars that lived and died before the Sun formed. This metallicity was just right for forming rocky planets like Earth. If the solar system had formed earlier, when the galaxy had lower metallicity, rocky planets might have been smaller or might not have formed at all. If it had formed much later, higher metallicity might have led to different planetary system architectures. The The timing of the solar system's formation in a galaxy with moderate metallicity might be important for life's development. The dust grains found in meteorites provide direct samples of supernova ejecta. Some grains, called pre-solar grains, formed in the outflows of dying stars or in supernova ejecta before the solar system formed. These grains can be identified because their isotopic compositions differ dramatically from the average solar system composition, reflecting the nuclear processes in their source stars. By analyzing pre-solar grains, scientists can learn about specific stellar events that occurred before the solar system formed. Some grains show isotopic signatures indicating they came from supernovas. Others came from red giant stars that shed their outer layers as planetary nebulae. Each grain is a tiny messenger from a specific star that died billions of years ago, carrying information about nuclear processes that occurred in extreme environments we can only study theoretically. Chapter 18: Supernovas and Cosmic Rays. One of the most important but least appreciated roles of supernovas is the acceleration of cosmic rays. Cosmic rays are high-energy particles, primarily protons and atomic nuclei, that zip through space at speeds approaching the speed of light. Despite their name, they're not rays but particles, and they permeate the galaxy. Cosmic rays were discovered in 1912 by Victor Hess, who flew instruments in a balloon and found that radiation levels increased with altitude, indicating the radiation came from space rather than Earth. For decades, the origin of cosmic rays remained mysterious. Today, we know that supernovas are the primary source of cosmic rays up to energies of about 10 to the power of 15 electron volts, far beyond anything achievable in human-made particle accelerators. The acceleration mechanism involves the shock waves produced by supernova explosions. When a shock wave propagates through a medium, it creates a discontinuity where particles can be accelerated through a process called diffusive shock acceleration, or Fermi acceleration, after Enrico Fermi, who first proposed a similar mechanism in the 1940 seconds. Here's how it works. A charged particle, say a proton, encounters the shock wave. Magnetic fields in the medium scatter the particle, causing it to cross back and forth across the shock many times. Each time it crosses, it gains a little energy from the bulk motion of the gas. This is like a ball bouncing between the front and back walls of a truck that's accelerating. Each bounce adds energy to the ball. After many crossings, the particle has gained substantial energy and eventually escapes the shock region, flying off into interstellar space as a cosmic ray. The process is stochastic, meaning most particles gain moderate energy, but a few gain enormous amounts. This produces a power law energy distribution, where the number of particles decreases as energy increases, but extends to very high energies. Supernova remnants are the most efficient cosmic particle accelerators known. The Fermi acceleration process can boost particles to energies millions or billions of times higher than their initial thermal energies. Observations of supernova remnants at X-ray and gamma-ray wavelengths show the telltale signatures of high-energy particles, confirming that acceleration is occurring. The highest energy cosmic rays, above about 10 to the power of 15 electron volts, probably don't come from supernova remnants. These ultra-high energy cosmic rays might originate from more exotic sources like the jets of active galactic nuclei, or possibly from the decay of supermassive particles left over from the early universe. But below this energy, supernovas appear to be the dominant source. Cosmic rays play several important roles in the galaxy. They carry energy, contributing to the pressure that supports the galactic disk against gravitational collapse. They heat interstellar gas, affecting cooling rates and star formation. They drive chemical reactions in molecular clouds, ionizing molecules and enabling chemistry that wouldn't otherwise occur in the cold, dense gas. For life on Earth, cosmic rays are both a hazard and a necessity. The hazard comes from their ability to damage biological molecules, including DNA. Earth's atmosphere shields us from most cosmic rays, and our magnetic field deflects many charged particles. But some cosmic rays reach the surface and can cause mutations. The necessity comes from cosmic rays' role in atmospheric chemistry. Cosmic rays ionize molecules in the upper atmosphere, creating ions that can seed cloud formation. Some researchers have proposed that variations in cosmic ray flux, perhaps correlated with the solar system's motion through the galaxy, might influence Earth's climate by affecting cloud cover. This hypothesis remains controversial and is still being investigated. Chapter 19. The Ultimate Fate. As we've explored the spectacular deaths of stars and the creation of supernovas, we've seen that massive stars end their lives in blazing glory, scattering their enriched material across space. But what about the very long-term future? What happens to neutron stars and black holes over cosmic timescales? Neutron stars, born hot from their violent formation, gradually cool over millions of years. They radiate away their heat as neutrinos and photons, eventually becoming cold, dark objects. But cold is relative. Even after billions of years, a neutron star's temperature remains thousands of degrees, far hotter than any star's surface, but cool by neutron star standards. As neutron stars cool, their internal structure might undergo phase transitions, rather like water freezing into ice. The superfluid in the interior might transition through different states, and if quark matter exists in the core, it might undergo changes as the temperature drops. These transitions would release small amounts of energy, briefly warming the neutron star or causing subtle, observable effects. Isolated neutron stars, those without binary companions, simply fade from view as they cool. After a few 100 million years, most pulsars have slowed their rotation so much that they no longer produce detectable radio emission. They become invisible, wandering through the galaxy as silent remnants of ancient stellar deaths. But neutron stars in binary systems can have extended active lives. If a neutron star has a companion star, it can accrete matter from that companion when the companion evolves into a red giant. The accreted matter spirals onto the neutron star's surface, releasing enormous amounts of energy as X-rays. These X-ray binaries can remain bright for millions of years as long as the mass transfer continues. If a neutron star accretes enough matter, its mass can increase beyond the maximum mass that neutron degeneracy pressure can support, approximately 2 to 3 solar masses depending on the equation of state. When this happens, the neutron star collapses into a black hole. This is one way to create low-mass black holes that couldn't form directly from core collapse. Black holes, unlike neutron stars, don't cool and fade in the conventional sense. They don't have surfaces that radiate heat. Instead, they slowly evaporate through Hawking radiation, an extremely weak quantum mechanical process. For stellar mass black holes, the Hawking temperature is less than a billionth of a degree above absolute zero, far colder than the cosmic microwave background radiation that permeates space. This means that stellar black holes are currently growing, not shrinking, as they absorb more energy from the cosmic microwave background than they emit through Hawking radiation. Only in the far future, after the universe has expanded and cooled so much that the cosmic microwave background temperature drops below the black hole's Hawking temperature, will black holes begin to evaporate. The timescale for a stellar mass black hole to evaporate completely through Hawking radiation is approximately 10 to the power of 67 years. This is incomprehensibly long, far exceeding the current age of the universe. To put it in perspective, If you started counting at 1 per second at the Big Bang and continued until now, you'd have counted to about 10 to the power of 18. A black hole's evaporation time is 10 to the power of 49 times longer than that. In the unimaginably distant future, after all stars have burned out, after galaxies have dispersed or merged, after even protons have decayed, if they do, black holes will be among the last structures remaining in the universe. One by one, they'll evaporate, taking 10 to the power of 100 years or more for the most massive ones, leaving behind only a cold, dilute sea of photons and other particles. But this is so far in the future that it's almost meaningless to discuss. The universe we know, filled with stars and galaxies, will persist for trillions of years. We live in what might be called the stelliferous era, the age of stars, when the universe is young and vibrant. Supernovas will continue illuminating the cosmos for trillions of years to come. Chapter 20: Witnessing Cosmic Majesty. As we come to the end of our journey through the life and death of stars, it's worth reflecting on what these spectacular events mean for our understanding of the cosmos and our place within it. Supernovas remind us that the universe is dynamic and ever-changing. Stars are born, shine for a time, and die, often spectacularly. The atoms in our bodies have been through multiple cycles of stellar birth and death, forged in stellar furnaces and scattered by supernova explosions. We are made of stardust, and supernovas are the mechanism that spreads that stardust through space, making new generations of stars, planets, and life possible. The study of supernovas combines nearly every branch of physics and astronomy. Understanding these explosions requires nuclear physics to describe fusion reactions and nucleosynthesis, particle physics for neutrino behavior, fluid dynamics for the collapsing core and expanding ejecta, general relativity for the strong gravitational fields, and observational astronomy across the electromagnetic spectrum. This interdisciplinary nature makes supernovas particularly rich subjects for research. Each new observation, each refinement of theory, impacts multiple areas of knowledge. The next galactic supernova, when it occurs, will be the scientific event of the century, studied by thousands of scientists using every available instrument and technique. For those of us who simply gaze up at the night sky, supernovas represent the ultimate cosmic fireworks, nature's most spectacular displays. When Betelgeuse eventually explodes, people around the world will look up in wonder at a brilliant new light in the sky, just as humans have done for countless generations when rare supernovas appeared. But beyond the spectacle, supernovas offer profound lessons. They teach us that even the most massive and powerful structures in the universe have finite lifetimes. They show us that destruction and creation are intertwined, that death gives rise to new life. They remind us that we are connected to the cosmos in the most fundamental way, that the atoms in our bodies were forged in stellar furnaces billions of years ago. Tonight, as you drift into sleep, imagine a massive star in its final moments. Deep inside its core, millions of years of steady nuclear burning have built up layers of progressively heavier elements, from hydrogen through helium, carbon, oxygen, silicon, and finally iron. The star has run out of options. No more fusion reactions can provide energy to support it against gravity's relentless pull. In less than a second, the core collapses. Matter falls inward at a quarter the speed of light. The core becomes so dense that atomic nuclei touch. Neutron degeneracy pressure and the strong nuclear force bring the collapse to a sudden, violent halt. The outer core rebounds, creating a shock wave that propagates outward. Hours later, the shock wave reaches the star's surface. The star's outer layers, heated to billions of degrees, explode outward at thousands of kilometers per second. For a few weeks, This single dying star outshines an entire galaxy containing hundreds of billions of stars. Its light, carrying the news of this cosmic catastrophe, races outward through space at the speed of light, traveling for centuries or millennia until it reaches the eyes of astronomers on a small planet orbiting an ordinary star in a distant part of the galaxy. And in that moment, across the vastness of space and time, we bear witness to the death of a star and the birth of something new. The heavy elements created in that explosion will enrich the interstellar medium, eventually becoming part of new stars and planets. Perhaps billions of years from now, those atoms will be incorporated into living beings who gaze up at their own night sky and wonder about the stars. This is the magnificent cycle of stellar life and death, a cosmic dance that has been playing out for billions of years and will continue for trillions more. We are privileged to live in an era when we can not only observe these events but understand them, tracing the physics from the quantum realm to cosmic scales, from nuclear reactions in stellar cores to shock waves spanning light years, from the creation of atoms to the birth of planets and the emergence of life. Supernovas are more than just stellar explosions. They are the forge where elements are created, the trigger for new star formation, the laboratory where physics is pushed to its extremes, and the proof that we are intimately connected to the cosmos. When we study supernovas, we are studying our own origins, tracing the path from simple primordial hydrogen to the complex chemistry that makes life possible. So sleep well tonight, knowing that you are made of star stuff, that every breath you take contains atoms from dying stars, that the iron in your blood and the calcium in your bones were created in supernovas that exploded long before Earth existed. You are part of the universe's great story, a story of transformation and rebirth, of death giving rise to life, of simple elements combining to create complexity and consciousness. And somewhere out there, at this very moment, another massive star is approaching the end of its life. Its core is filling with iron. The final countdown has begun. Within days or weeks or years, that star will explode, briefly becoming one of the brightest objects in the universe, scattering its enriched material across space and continuing the eternal cycle of stellar birth, life, death, and rebirth. That explosion, when it occurs, will be witnessed by astronomers across the galaxy, by beings we may never know, on worlds we cannot imagine. And perhaps they too will look up in wonder and ask the same questions we ask. What are we? Where did we come from? How do we fit into this vast and beautiful cosmos? The answers, written in starlight and supernova fire, are there for those patient enough to seek them. Thank you for joining me on this journey through the spectacular deaths of stars. If you found this exploration enriching, please consider liking this video and subscribing to Astromind for more deep dives into the wonders of our universe. Until next time, clear skies and peaceful dreams among the stars.